sent out in the mail.
Alrighty, good morning everybody. Welcome back to Calc 1 on this lovely day. Plan for today is I have a quiz for you on Standard 10, and then we are going to jump into Standard 11. Take everything we've been doing for the past few, and we're going to take everything we've been doing for the last few weeks and twist it around and go the other way by taking anti-derivatives. My next office hours are on Monday at 11 and at 2. And as far as homework goes, I posted a web work, homework 14, that will be due on Wednesday. Yes?
Isn't there homework 13 due on Monday?
Yeah.
Is there a homework 13 due Monday? There's a homework 13 due Monday.
Okay, make sure.
I forgot to check before class to make sure I knew what's coming up. All right, so 4 friends one day who've been doing really well in calculus decide to take a weekend road trip instead of studying for the final. Clearly not Hillsdale students. Not surprisingly, they drink too much, oversleep on the morning of the final, and get back to campus after the exam is already over. One of them concocts an explanation and asks for the professor's mercy. "We went to my parents' cabin for the weekend so we could have a quiet place to study. Driving back on Monday morning, we got a flat tire. We didn't have a spare and it took hours for help to arrive." The professor sympathetically says, "Oh, I understand. Come back tomorrow morning and I will allow you to take a makeup exam." So the next day, the professor seats the students in 4 corners of the large lecture hall. The tests are only 1 page long. They're already on the desk. And the professor tells the students to begin. On the front side of the paper is just 1 question involving taking a derivative, and all 4 students answer it easily. On the back is an even simpler question. Which tire was it? All right, I'm going to go ahead and pass out the Standard 10 quiz. So go ahead and put everything away. It is quiz time. Sorry, these being a little sticky.
Making trees. Got my tree building. Love it. Oh yeah.
Go ahead and take a few seconds to finish up your thoughts. Okay, and pass your quizzes in, please. Pass your quizzes in, please. Hey, keep your pencil. Need it. All right, time for standard 11. Say what?
Quiz out.
Oh, he cleared it with me ahead of time. Brad have had some cutting comments for him.
Must have been a harder one, I think.
Okay, he has a big event he has to go. Alright, hope that quiz wasn't quite so computationally taxing as the previous one. Plan for today is we are going to start talking about antiderivatives, which is basically what happens when instead of taking a derivative, you go backwards and find a function whose derivative is your original function. So here's the scoop. I want to look at the function f of x equals 6x plus 2. And what I'd like for you all to do is to work your way through the first page of this packet with someone with your neighbors. So with maybe work in pairs with someone sitting around you. And your goal is going to be to find 3 functions whose derivative is equal to f of x, and then to answer a couple of questions about those functions, like what relationship do they all have with each other, and see if you can answer the question of how many functions are there out in the world somewhere that have a derivative of 6x plus 2. So go ahead and take a couple minutes, talk to your neighbors, and see what you can make of this front page.
I have one. I copied it off.
I don't know. There's technically there.
Can you do
Hey.
one?
Buddy.
For what? Can we do Toki, you could do 12x over 2.
Yeah, but that simplifies. That simplifies. Let's say that.
Oh, because we cut it out. We can add a link. That's a great idea.
Oh, negative 12x over 2.
What?
Yes. Because then we're just adding constants.
It would be a negative 1/2. And the negative 1/2 times negative
We could add
12
like 5 constants.
is positive
Let's add
6.
So did you say?
You're just memorizing.
No, I'm confused. what
Square
you're
root of
saying.
32.
Square root.
It would be negative 12x over 2.
Are all those different functions?
Plus
Do they all have a
2x.
derivative of 6x plus 2? Sure.
Infinite.
Sounds good to me.
Way to go, Bestie.
When I say they have to be 3 different functions, I don't mean they have to be extremely different from each other.
Like, I don't know.
Infinite.
Just put in a different value and see.
True.
Can you do that?
Nope. That doesn't. No.
Can you do
That doesn't work.
Square plus 2 plus 1, 2, just change the sign.
Are those all different functions?
I'd say so.
Do they all have the derivative of 6x plus 2?
They should, yes.
Then I'm on board.
You figured it out.
Nice.
I will not take that.
That doesn't work.
Why?
Because you have to take the antiderivative.
Yeah. If you do negative 12 times negative 1/2, is that not so?
You know the function for this power. The constant change you get.
Okay, sounds like things are quieting down. Anybody like to share a function that they found whose derivative is 6x plus 2? I heard quite a few as I was listening around there. Let's see.
3x squared plus 2x.
3x squared plus 2x. Let's see, if we differentiate, power rule says we'll get 6x plus 2. I'm on board. Riley?
3x squared plus 2x plus 1.
3x squared plus 2x plus 1. Let's see, if we differentiate, we'll get 6x plus 2 plus 0, so 6x plus 2. I'm on board. Avery?
3x squared plus 2x plus the square root of 32.
3x squared plus 2x plus the square root of 32. What's that, 4 radical 2? If we differentiate, we'll get 6x plus 2 plus 0. Like it? Anybody have any others?
3x squared plus 2x plus 2.
Sure. I'm not gonna write that one down, because I think you all get the idea. The one I had, for the record. All right, Josh, help me. The one I had was f5 of x equals 3x squared plus 2x minus 9,000 pi to the power of e to the power of pi.
Just wait.
That looks scary, but it's a constant, so the derivative is 0, so it doesn't actually affect anything. Did anybody have a function that didn't have 3x squared plus 2x in it? Oh, slacking off, huh? Just trying to go the easy route. Good, because there are no other functions. Well, there are many other functions, but they all have 3x squared plus 2x in them. What do you notice about the relationship between all of these functions whose derivative is 3x, or blah, 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 whose derivative is 6x plus 2? Right?
They all have like the same shape, they're just gonna be shifted up or down on the graph.
Ooh, okay. So graphically, if we were to graph all of these, how does that look like? That's going to have a root of 0 and a root of x plus 2 is 0, negative 2/3. So graphically, they're all going to look something like this. So yeah, that's an interesting observation, Ollie, that graphically they're all the exact same graph, but the only difference between their graphs is that they're shifted vertically up or down from each other. But they all have the same slope at every single point. At any point you might try and take the derivative, say like at, I don't know, whatever value of x this is. The tangent line at that value of x on any graph is always going to have the same slope. It'll have a different y-intercept, but the same slope, corresponding to the fact that all of these are functions who share a common derivative. How about any observations relating to what do the formulas for F1, big F1, big F2, big F3, etc. look like? Josh?
The only thing that changes is the constant at the end.
Yeah, they're all the same except for the constant terms. So let's say in terms of their formula, they all are the same. Except for their constant terms. Big F1 technically has a constant term of 0, constant term of 1, square root of 32, 2, negative 9,000 pi to the e to the pi. But other than those constant terms at the end of the functions, they all have the same pieces otherwise. These 3x squared plus 2x terms. And so finally, can we say something about how many functions are there that are going to have a derivative of 6x plus 2? Fair?
Is it infinite because there are an infinite number of constants that can be added at the end?
Ooh. So basically you say, since there's infinitely many choices of constant terms that come at the end of this, we could just plug in one of infinitely many constant terms and get an infinite family of functions that way? Does that sound good to everybody? Yeah, I think so. It's going to turn out to be the case that there's not one, not 5, but infinitely many functions whose derivative is equal to 6x plus 2. And as Vera pointed out, we can find infinitely many by just taking 3x squared plus 2x and then adding any constant term to the end of that we might like. So I'll say any function of the form big F of x equals 3x squared plus 2x plus c for some constant c works. And since there's infinitely many numbers we could plug in for c, even if we just wanted to restrict ourselves to nice numbers like 1, 2, 3, 4, 5, etc., or if we wanted to get crazy and go with square root of 32 or negative 9,000 pi to the e to the pi, there's infinitely many values we could plug in for that constant term at the end that aren't going to affect the derivative, because when you take the derivative of a constant term, no matter what constant you're looking at, it's just going to be 0 and not affect the derivative of the overall expression you're looking at. And to say, and there are infinitely many values we can plug in for c. Congratulations, you just took your first antiderivatives. So, flip to the second page. So it's going to turn out to be the case that when you take an antiderivative of a function like 6x plus 2, when you take a derivative, you do the power rule, chain rule, product rule, what we've been doing for the last few weeks, which would give us 6 in this case. But when we take an antiderivative of a function, we're looking for functions whose derivatives are the original function. So in this case, big F1, big F2, big F3, big F4, big F5, all of these are going to be antiderivatives of little f of x equals 6x plus 2. So in general, we can say that a function big F of x is an antiderivative of little f of x if the derivative of big F of x is equal to little f of x. It's a function that if you were to differentiate, you would get little f of x. So in other words, you can say that big F of x is an antiderivative of little f of x if little f of x is the derivative of big F of x. Why do you think I'm using this line? So here I'm trying to be careful, remember my English lessons from back in the day, and I'm trying to be very careful in my word choice here. And that I say big F of x is an antiderivative of little f of x if little f of x is the derivative of big F of x. Why do you think I'm using these articles specifically? An antiderivative versus the derivative. Rachel?
Because big f of x isn't the only antiderivative, but little f of x is the only.
Yeah, in general, when we talk about antiderivatives versus derivatives, a function little f of x can have infinitely many antiderivatives, but in general, it'll only have a single derivative. Like if I were to ask you, find all the derivatives of little f of x equals 6x plus 2, Tyra, what would be, give me as many derivatives of little f of x equals 6x plus 2 as you can.
Well,
Just plain old derivatives this time.
derivatives of 6x plus 2, sorry.
Mhm.
Of 6x plus 2.
Mhm.
Oh, well, it would just be 6.
That's the only one?
Yes.
Yeah, Exactly. Turns out a function can only have a single derivative, which you find by doing all the stuff we've been looking at for the past several standards. 6x plus 2 just has a plain old derivative of 6, but it can have infinitely many antiderivatives, which is why I'm using this language here. F of x will have only one derivative, or potentially no derivatives if little f of x is not a function that's differentiable everywhere, but can have infinitely many antiderivatives. Infinite, I can spell. Any questions or comments so far? Dr. Ursel, why do we care about looking for antiderivatives? It's going to turn out to be very handy for us when we look at some problems in a couple standards from now, how to find antiderivatives of functions. If you remember when we started out, we asked the question of, if you know that something's distance, if you have a distance function for something, you can differentiate it to find instantaneous velocity at a given point. It's going to turn out to be the case that if we know how to take antiderivatives, we can work backwards and answer questions of, say, if we know how fast something is moving, if we have a formula for velocity, we can take antiderivatives to find formulas for what is the distance traveled. That's going to be coming a couple standards down the line. So, turns out that the observation you all made for little f of x here, that all of our antiderivatives are exactly the same except for the constant term at the end, it's going to turn out to be the case that that's going to be true for every function, not just 6x plus 2. That if you know that you have two antiderivatives of the same function, then they have to be the same except for their constant term. So I'll write this down as a theorem. We could say that if big F1 of x and big F2 of x are both antiderivatives of the same function, little f of x, then we know for some constant c, big F1 of x has to be equal to big F2 of x plus that constant c. They have to differ by some constant term. Another way to write that would be to say if you took the difference of the two functions, big F1 of x minus big F2 of x, it would always be some constant expression. The x terms would cancel out and just leave you with something like, I don't know, 1 or 5 or 9,000 pi to the e to the pi. So some constant term is going to appear. So what this tells us, we can say that if we have a function like little f of x equals 6x plus 2, Emily, what is your favorite antiderivative of 6x plus 2? You can use one of the ones we have or come up with your own if you like. 3x squared plus 2x plus 2, going with Josh's? Sounds good. We could say that if little f of x equals 6x plus 2, then since one antiderivative of little f of x is big F of x equal, let's say big F, which one was that, 4? Of x equals 3x squared plus 2x plus 2. A little hurt, you didn't choose my one with the pi to the e to the pi, but that's okay. Since that's one antiderivative, any other antiderivative is going to have to be equal to that same one plus some constant term. And the other antiderivative of little f of x will have formula big F of x equals 3x squared plus 2x plus 2 plus c for some constant c. In other words, once you know one antiderivative of your function, you know all the antiderivatives of your function. They're just going to be that first antiderivative plus any constant term. Or minus the constant term if you want to make your constant term negative. And that's true no matter what function you are looking at. Any questions, comments, or concerns? So we have a special name for what happens if you look at a function and you find all the antiderivatives of that function. And we're going to call that taking the indefinite integral of that function, or integral for short, where we can say that the indefinite integral of a function f of x is the family of all antiderivatives of f of x. And the notation that we're going to use to write out what it means to take the indefinite integral is going to look like this. We're going to have this swanky symbol here. I'll give you a hint. It's an S, but we've stretched it out vertically. And if we write that swanky symbol, which this is going to be the integral symbol, then if we write out integral symbol of f of x, integral of f of x dx, that's going to be the family of all antiderivatives of f of x. Or the family of all functions whose derivative are plain old f of x. So as an example, if we wanted to say, for instance, find the integral of 3x squared minus 4x dx. Oops, sorry. Let's not do that one first. Let's do this one. Sorry, that's a typo in the packet. It's supposed to say 6x plus 2 for the first one. What would the family, what can we say about all of the functions whose derivative is 6x plus 2?
3x squared plus 2x plus c.
Yeah, they're all going to have the form 3x squared plus 2x, and then we're going to write a plus c at the end, where c is allowed to be any constant. And so when we write it out like this as 3x squared plus 2x plus c, we're accounting for the fact that any antiderivative of 6x plus 2 is going to have this form. It's going to have a 3x squared term plus a 2x term, and then it's going to have some other constant term tacked on to the end. Or c could be 0 if we want big F1, 1 if we want big F2, 2 if we want to be lame and use Emily's favorite constant of plus 2. No offense to Emily or Josh. Or to be cool like me. But any antiderivative of 6x plus 2 is going to look like this. And so we can say that this is the family of all of our antiderivatives. Couple comments. Dr. Gerstl, what is this? We have a dx appearing at the end here. We're going to go into heavy detail as to what dx represents in like 8-ish standards from now. But for now, what I want you to know when you see this dx term appearing at the end of your integral, that's telling you what variable you're integrating with respect to. You're integrating with respect to the variable x. Just like we can say when we differentiate with we can differentiate with respect to a variable x. So just to give you an example of why this dx at the end of our integral is important, let's say we wanted to take the integral of, I don't know, x times t with respect to x. So here, the dx means that we're treating x as a variable and t as being some constant term. So if t is just a constant, and we want to find all the functions whose derivative with respect to x is going to be x times t, what would we find? Maybe let's start by asking a simpler question. If I wanted to find all functions whose derivative is just plain old x, what would we get? When?
X squared over 2.
Yeah, we get 1/2 x squared. Plus
Plus e.
plus constant. So if we have this other variable t thrown into the mix, assuming t is just some constant, well, constants, spoiler alert for next page, get pulled along for the ride. It's going to be 1/2 x squared times t plus c. Since if we were to differentiate with respect to x, 1/2 x squared times t plus c, we get 2/2 x to the first, which is just x, times t plus a constant. Or, nope, not plus constant anymore, because we differentiated it and it's become 0. We've also, if I was feeling really like a jerk, I could also ask you, what's the integral of x times t with respect to t? In other words, if we were to now treat t as our variable and x as a constant, man, you want to give it a shot?
Sure. Xt squared over 2 plus c.
1/2 t squared times x plus a constant. I like it. And that's because if we take the derivative with respect to t of 1/2 t squared times x plus c, we're just going to get back x times t. So the reason we have this sort of dx or dt term at the end of our integral is basically, for now, we're going to be treating as a placeholder to say, what is the variable we're differentiating with respect to? Because we could potentially have functions that have multiple variables going on, and if it says integrate with respect to t, that means treat t as a variable and x as a constant. Whereas if we're integrating with respect to x, if we have a dx at the term, that means treat x as your variable and t as your constant. Behold, the number one most common mistake I've seen in a Calc 1 class. forgetting to write dx at the end of your integral. Or dt, whatever variable. Just saying, oh, the integral of 6x plus 2 is 3x squared plus 2x plus c. No, bad. Always remember to write your dx or dt or d whatever variable. D omega if you're feeling really cheap. It can happen to any one of you. It will happen to some of you. Don't let it happen to you. Number one biggest mistake. And yes, that is the sort of mistake where if you forget to write your dx, it's not the sort of thing you're going to lose a mastery over. But it is the sort of thing that will cause me to write out dx after each one of your integrals and write like a frowny face and make you go from an m to an m minus. And if you do it too many times, and I feel particularly aggrieved, it could, yes, take you from an m minus to a j plus. Just like those of you who think it's cute to stop writing your limit as before you actually take the limit. Don't let it happen to you. Any questions or comments on what it means to take an indefinite integral? Dr. Gerstel, you call it an indefinite integral. Does that mean there's a definite integral? Ho, ho, ho. Yes. There is a thing called the definite integral, but we're not going to see that until like I think that's like the last 4 standards. We're mainly focusing on another type of integral called a definite integral, which is related to this by the fundamental theorem of calculus, which we will see in a month or 2 from now. Lise, do you have a question?
So a lot of the stuff we've been looking at is like fairly simple, like you can figure out what the antiderivative is easily, but when it comes to something like the chain rule, how do you even recognize what steps it took to get there just by the end result?
So if I were to give you something like the integral of, and say, oh, the integral of 2x e to the x squared dx, I almost just made my own mistake, turns out to be, oh, that's just e to the x squared plus c, because if we differentiate this, we'll get e to the x squared times the derivative of x squared, which is 2x. How would we, if I gave you an integral like that, how would you know how to do the chain rule backwards? We're going to have a standard related to specifically that towards the end. Where it's the way to undo the chain rule is through a technique called a U substitution. But we're not going to do that for quite a while. Right now, pretty much everything we're going to be anti-differentiating in this standard is going to be the stuff we differentiated in standard 5. So stuff of like you could differentiate just using the power rule, sum and difference, constant multiple rules. And we'll start looking at more and more complicated integrals and more complicated expressions as time goes on. But I'm not going to start by asking you something like that because that is very scary. And I recognize that. Spoiler alert, it's a little bit scary for me too. Yeah, good question. How would you recognize that? Through lots of practice, and we will be having that later on. Any other questions or comments for now? And yes, there is a rule for how to do the product rule backwards too. And no, there is not a rule for how to do the quotient rule backwards, because the quotient rule backwards would be utterly terrifying. Okay, let's see. Let's look at a couple more examples. Before we flip the page, if I were to ask you, what would be the integral of 5 with respect to x?
C.
Say what?
5x plus c.
5x plus c? Like so? Yeah, because if we differentiate 5x plus any constant with respect to x, we're just going to get back plain old 5. All right, Josh, you're so clever. We integrate 5 with respect to s.
Job, coach.
Well, since you asked, yes.
5s plus c.
Indeed. We can switch up the variable that we're differentiating with respect to, and that'll change the types of functions we get as our antiderivatives. Usually it'll be either dx or dt in this class, and usually just dx. dt will come up if we're looking at word problems in a couple standards from now. So don't worry too much about there being lots of different variables floating around. It doesn't really change too very much. How about this one? Integral of -1 over t squared. This is a bit trickier. Oh, except Mackenzie doesn't think so.
Well, you could rewrite it as negative t to the negative t squared. And then the antiderivative would be 1 over t.
Let's see, 1 over t. So you're claiming that if we take an antiderivative of -t to the -2, we'll get t to the -1. Let's see, if we differentiated that with respect to t, we get a -t to the -1 minus 1, which is -2. And so you claim that 1 over t is going to be our indefinite integral?
Plus c.
Plus c. I like it. Yes, 1 over t. Nice job, Mackenzie. That was a good observation, that if we take -1 over t squared and just rewrite it so it has a negative exponent, then you could sort of recognize that you could take antiderivatives of that by just looking at t to the -1, because the derivative of t to the -1 will give us -t to the -2. Questions or comments? All right, I want to talk about how to get dressed in the morning. Specifically, you want to put on socks and shoes. When you put on socks and shoes, does it matter what order you put them on in? Yes? Josh, when you put your socks and shoes on, which do you typically put on first?
My socks,
You put your socks on, and then your shoes?
most days.
Most days. Seems reasonable. All right, Josh, answer me this. When you're all done for the day, and you want to take your socks and shoes off, which ones do you take off first?
Shoes.
Your shoes. But didn't you put your socks on first? Why don't you take your socks off first?
My shoes are on over my socks.
Oh, your shoes are on over your socks. So when you take your socks and shoes off, you have to take them off in the opposite order. How about that? Dr. Hurstel, where on earth are you going with this? So what I'd like to do next is to find a formula for what happens if we take the antiderivative, or if we take an indefinite integral of an arbitrary function of an arbitrary power function. And this is going to give us our reverse power rule. How many times am I going to make that before I spin around and make myself dizzy? So, first of all, I want to look at how you do the power rule, just as a quick review. If we were to differentiate the function x to the n, what are we going to get, according to the power rule? Rachel?
N times x to the n minus 1.
N times x to the n minus 1. Sounds to me, Rachel, like you just did two things there to get from x to the n to n times x to the n minus 1. What were the two things you did?
We multiply by n and we also subtract 1.
Okay, so the first thing we did was we multiplied by the exponent. And then, sounded like you subtracted 1 from the exponent after you multiplied by it. does it matter what order we do these in? If we subtracted 1 from the exponent and then multiplied by it, would that give us something? Would that give us the same thing or something different? I think it would be different, because if we subtracted 1 first, we get, and then multiplied, we get n minus 1 times x to the n minus 1. We'd start by subtracting 1 to get from x to the n to x to the n minus 1. And then if we multiply by that exponent, we get n minus 1 times x to the n minus 1. So the order here matters, that we have to multiply by our exponent, and then we have to subtract 1 from it. Dr. Ursula, what does this have to do with taking our shoes and socks on and off? So Josh, you told me that when you take your socks and shoes off in the evening, you take them off in the opposite order to which you put them on. Yeah?
Yeah.
Seems going to be true for when we undo the power rule and do the power rule backwards. And that in order to differentiate a power function, we have to multiply by the exponent and then subtract 1 from our exponent. So to do the reverse power rule backwards, we're going to do the same 2 steps, or technically we're going to undo the same 2 steps, but this time we're going to do them in reverse. Because the last thing that we did in order to do the power rule was to subtract 1 from our exponent. If we want to undo these 2 things, we have to start by undoing this second thing, subtracting 1 from the exponent. So how can we undo the act of subtracting 1 from our exponent? In other words, if we've subtracted 1 from the exponent, what do we have to do to our new expression to get back what we got before step number 2 here? What?
Add 1 to the exponent.
Yeah, to undo subtracting 1 from the exponent, we're going to add 1 to the exponent. And by doing that, we're going to undo the action of subtracting 1 from it. If we think about this as putting on your socks and then putting on your shoes, the first thing you do if you want to undo all of that is to take your shoes off. Undo the second action first. And then our second step is going to be undoing the action of multiplying by whatever our exponent is. Someone other than Wynn. How do we undo the action of multiplying by our exponent? How?
You divide by the
Divide by the exponent? Sam? Does that sound right? Yeah, I like it. Divide by your new exponent. If this was putting on socks and this is putting on shoes, to undo that, you start by taking off your shoes and then you take off your socks. And so, see what that means. If we want to integrate x to the n, we're going to start by adding 1 to our exponent. Go from x to the n to x to the n plus 1. And then we want to divide by our exponent, which means dividing by n plus 1. So in the end, in order to integrate x to the n, we're going to get x to the n plus 1 divided by n plus 1. What am I forgetting? Oh my gosh, plus c. All right, would you like a bonus joke of the day?
Yes.
What be a pirate's favorite letter? R? Nar, it be the C. So, if we integrate x to the nth power, we're always going to get x to the n plus 1 over n plus 1. So just do a quick couple examples here, putting this into practice. If we wanted to integrate, say, x squared, we could add 1 to our exponent, get x cubed, divide by the new exponent to get 3, and we could write this as 1/3 x cubed plus c if we want, or just x cubed over c, or x cubed over 3 plus c, however you want to write that. Hannah.
Yes.
This Dave we called me, sir.
Sorry.
I'm just joking. What would we get if we wanted to integrate x to the -7?
The exponent would be -6. And then it'd be 1 over -6
-1 x to the -6
plus c.
plus constant. I like it. So we can integrate power functions like this by just adding 1 to the exponent and then dividing by the new exponent. All right, Josh, got one for you. If we wanted to integrate x to the -1, or in other words, 1 over x.
X. Let's see.
I think the derivative of x plus c is just going to be 1, not 1 over x. So if we add 1 to our exponent and then divide by it, what's going to happen?
No.
If we add 1 and then divide by it, we get no. No is not a function that I'm aware of, but okay. Zach?
You want me to give you the antiderivative of that?
Yeah, give me an antiderivative.
Natural log of x plus c.
Natural log? Where did that come from?
Well, that's standard.
Oh my gosh. Josh, I'm trying to get you. I was trying to get you to fall for the trick where you add 1 and then divide by 0, and then I could say, don't divide by 0 in my class, and throw a piece of chalk at you. Zach, however, has noticed something interesting. He thinks that this is going to come out to natural log of x plus a constant, which is interesting. And also wrong. Dr. Gerstle, why is that wrong? For very sneaky reasons we're going to talk about in the next standard. Spoiler alert, next standard is going to be taking integrals of that involve logs, exponential functions, and trig functions after we get through this stuff. So if you look in the packet on this page, turns out that sum and difference rules work just the same way they do for integrals and antiderivatives as they do for derivatives. And constant multiple rules work basically the same way. The integral of a constant times a function, you can just pull that constant out in front of your integral. So if, for instance, we wanted to integrate something like six x cubed minus 8x plus 4. According to the sum and difference rules, we could just integrate each one of these pieces individually. And according to the constant multiple rule, you could just pull the if we wanted to integrate 6x cubed, for instance, we could just integrate x cubed and then multiply whatever the integral of that is by 6. So what would we get if we integrated, just to start off, let's say 6x cubed? Anybody have any ideas as to if we wanted to integrate 6 times x cubed using the reverse power rule and the constant multiple rule, what would we end up with? Clark?
We'd have x
squared over 2 times, and then all of that times 6.
Be careful, you need to add 1 to
Oh,
our exponent, not subtract.
So x to the 4th over 4 times all of that times 6.
Like that. I like it. Yeah, because if we differentiated this, we would get 6 times, what, 4x cubed over 4, which would just come out to 6x cubed. Sounds good to me. How about integrating negative 8x? Sarah, you want to give that one a try?
Is it 4x squared?
Let's see, we're going to get minus 8 times x squared over 2, which I think will come out to a minus 4x squared when we simplify that in the next step. Yeah, I like it. And finally, how about the plus 4? Sam?
Plus 4x.
Plus 4x. Yeah. Very good. You didn't say it was plus 0. We're so used to differentiating constants and just getting 0 every time. But when we integrate a constant, we get that constant times x back. Not just 0 every time anymore. So when we integrate 6x cubed minus 8x plus 4, we get 6 times x to the 4th over 4 minus 8 times x squared over 2 plus 4x. Plus c. Second/third most common mistake in a Calc 1 course that I've seen. Forgetting your plus c at the end of your indefinite integral. Because we have to account for the fact that when we find the antiderivatives of 6x cubed minus 8x plus 4, there's not just one of them, there's infinitely many that all differ by this constant. And then I would probably simplify this to get, what, 6/4 is the same as 3/2, x to the 4th. As Tyra pointed out, this is going to give us a minus 4x squared plus 4x plus c as our final answer. So, anti-differentiating with like polynomials like this, it's pretty similar actually to differentiating them. You differentiate each piece separately when you have a sum like this or difference. You use the constant multiples out in front just get carried along for the ride. And instead of using the power rule, use the reverse power rule to integrate each of these pieces separately. By the way, remember when I said earlier I defined the indefinite integral to be the family of antiderivatives? I didn't say the collection of antiderivatives of f of x or the set of all antiderivatives of f of x. I said the family of all antiderivatives. You know why that is? They're all related. I think is the best explanation I can come up with. The other explanation I've come up with is mathematicians are weird antisocial types who think of functions as being their own family members because they're so used to hanging around them. All right, that's going to do it for today. When we come back on Monday, we'll look at some more examples of integration and putting what you all did today into practice. Hope you all have a good rest of your day, and I will see you all on, hope you all have a good weekend, and I will see you all on Monday. Take care.